Good morning. Okay, so let's get started. What I want to talk about today is an introduction to the last topic that we're going to be covering this semester. It's going to be the topic for this week and next week, and that is the topic called hypothesis testing. Now, we talked back in the first week of the semester about sort of the way this course is structured, and we have 3 exams and 3 main topics. So the first month or so of the semester, we covered descriptive statistics. We had an exam on that. Then we covered a few chapters on probability. We had an exam on that. And now we're into inferential statistics. And within the topic of inferential statistics, there's 2 main problems. So in inferential statistics, we talked last week about estimating parameters. And the other main topic within inferential statistics is testing the validity of hypotheses or claims. Now, a claim is some statement, some declarative statement that's statistical in nature, something that has to do with the mean or the standard deviation or the variance or the proportion or the median or some, excuse me, some statistical characteristic of a population. So estimation was not chapter 8, chapter 7. That was last. Estimation was chapter 7, and testing hypotheses or testing the validity of claims, well, that's chapter 8. Well, chapter 8, 9, 10, 8 through the end of the textbook, actually. If we were to do anything, any other chapters, we would continue on with this topic. So basically, and this is a somewhat complicated topic, but to sort of describe it in the simplest possible way, it's analyzing data to answer a yes/no question. So yes or no, does the available data support a hypothesis? So a hypothesis test, and this is the topic. This is like the topic of the problems you're going to be seeing this week and next week. A hypothesis test is a procedure or a method for testing a claim that's being made about some property of a population. So the first step in a hypothesis test is to be presented with a claim. Now that claim is going to be something involving a statistical characteristic or some population parameter. So for example, a claim could be the population mean is equal to some number C, or the population mean is not equal to some number C, or we could use an inequality. The population mean is greater than some number. The population mean is greater than or equal to some number. Mean is less than, or mean is less than or equal to some number. And we could also use the proportion. We're going to look at the mean and the proportion. So population mean, population proportion. Greater than or equal to, proportion is less than some number, or proportion is less than or equal to some number. So these are the options. Your claim is going to be a statistical statement that contains one of these 12 statements. Claims could also be made about any other parameter, the standard deviation, the median, the variance, etc., the correlation coefficient. We're going to be looking at only the mean and the proportion. Okay, so once we have a claim, excuse me, once we have a claim that's being made, and that's going to be given to you in a problem, the next thing to do is to establish your hypotheses, and there's going to be two of them. Okay, so establish the two hypotheses. And these two hypotheses, they're going to be called the null hypothesis The symbol for that is capital H with a subscript 0, the null hypothesis, and the alternate hypothesis. And the symbol for the alternate hypothesis is capital H with a subscript of 1. So H0 and H1. So your original claim is going to be one of these, right? And your hypotheses, well, they're going to, there's less options for those. So your null hypothesis. So basically your null hypothesis is the default hypothesis. It's basically the thing that you assume is true unless there's enough data to say otherwise. So it's like if you think about a court case, you go to court, and in this country, if you go to court, you are innocent until proven guilty. So you go into a court case under the assumption that you are innocent unless there's enough data. In that case, we would call it evidence. And if there's enough available data, if there's enough available evidence, then you discard that first hypothesis of innocence, and then you say, okay, this person is guilty. So you're innocent until proven guilty. That's what's happening with these hypothesis tests. You assume the null hypothesis is true unless you have enough sample data to suggest otherwise. Now, the null hypothesis is always a statement of equality. So it's going to be the population mean is equal to some number, or the population proportion is equal to some number, depending on the subject of the problem. So that is, there's no thought process behind this necessary. There's no options. The null hypothesis is always the parameter is equal to this number. Now, the alternate hypothesis is, it's basically your plan B. The null hypothesis is plan A, the alternate hypothesis is plan B, and that's going to be a statement that does not contain equality. So it can't contain an equal sign. It can't contain a greater than or equal to, or it can't contain a less than or equal to. So the alternate hypothesis will always be either the mean is not equal to some number, the mean is greater than some number, the mean is less than some number. Or if the problem is about proportion, it's the proportion is not equal to some number, the proportion is greater than some number, or the proportion is less than some number. So those are the options for your alternate hypothesis. Okay, so this is the beginning of the hypothesis test. Now, we're not actually going to be doing hypothesis tests this week. This week we're looking at the individual components of the test, and then next week we'll talk about the hypothesis testing specifically for the mean or for the proportion. Okay, so in terms of interpreting the original problem. Now I'm going to use the mean here, but you could replace the mu with a p if you're talking about proportion. The focus here is not so much on the parameter, it's on the symbol that we're using. So if the original claim is a statement that says the mean is equal to some number, then the null hypothesis would be, again, the statement of equality. And the alternate hypothesis would be, not H1, would be a statement that the mean is not equal to some number. Same thing for the, if the original claim is containing the symbol not equal to, mean equals some number, alternate hypothesis, mean is not equal to some number. If the original claim contains greater than or less than, then the alternate hypothesis is the same as the claim. So the null hypothesis is always a statement of equality, and the null hypothesis is the inequality. And finally, if the original claim contains a greater than or equal to symbol or a less than or equal to symbol, so mean is greater than or equal to C, mean is less than or equal to C. So if your original claim contains one of those symbols, your null hypothesis, again, is always a statement of equality. And your alternate hypothesis will be the negation or the complement of the claim. So if the original claim is greater than or equal to, the null hypothesis will be less than. And if the original claim is less than or equal to, then the null hypothesis will be greater than. this has to come first. So the null hypothesis and the alternate hypothesis should both be stated first before you do any hypothesis test. And again, like I said, the null hypothesis is always a statement of equality. Now comes the data. So once you are presented with a claim and you've established your null and your alternate hypothesis, now it's time to look at the data and determine, is the data strong enough to reject the default or the null hypothesis and potentially move on to accept the alternate hypothesis? That's what we call a hypothesis test, is that whole process of analyzing the data. And we're going to use as our as the backdrop behind this idea of a hypothesis test, we're going to use the normal distribution, much in the same way that we used it for confidence interval estimates. Okay, so number one, you're presented with a claim. So you write the claim using symbolic or mathematical notation. Once you have the claim, that determines your null and alternate hypotheses. Now, once you have those, then you want to convert the sample results into one single value that's used to represent the sample data. We call that a test statistic. So convert the sample data into a test statistic. So this test statistic, well, there's going to be 3 of them, depending on if we're using the, just like last week in chapter 7, depending on whether we're using proportion or if we're using the mean with knowledge of the population standard deviation, or if we're using the mean without knowledge of the population standard deviation. So again, just like last week, we have to consider both z values and t values depending on the distribution. So our test statistics are going to be, if we're doing proportion, it's going to be sample minus population. Sample proportion minus population proportion. And same thing. Oh, sorry, that should be a z, not p. That should be a z-score. And if we're using mean, it's sample minus population, sample minus population, and we divide that by the standard error. And we talked about standard error last week in chapter 7. So the standard error for the proportion is p times q over n under the square root. For the z-score, it would be sigma over the square root of n. And for the t-value, it would be s over the square root of n. So the same standard errors that we introduced last week. Okay, so your test statistic is going to have to be one of these 3. And now to perform the hypothesis test, we basically answer the question, do we or do we not reject the null hypothesis? So that's step 4. Determine whether or not to reject the null hypothesis. So this is a yes/no question. Do we keep the null hypothesis or do we reject it? And we answered this yes/no question by comparing the sample data, which is the test statistic, by comparing the sample data to something. And now there's going to be 2 methods for doing this. One is looking at critical values and one is looking at probabilities. That's 2 methods of doing the same thing. So we have the method of comparing the test statistic to the critical value. These are the same critical values that we used last week. So we could compare the test statistic to the critical value. So one of 2 things could happen. The test statistic could be bigger or the critical value could be bigger. So if the test statistic is farther from 0, then we reject the null hypothesis. If the critical value is farther from 0, we fail to reject the null hypothesis. So if the critical value is further from 0, then fail to reject. Okay, so this is the critical value method. And the other method is to compare the significance and the significance is alpha, the same alpha from last chapter, from last week. Compare the significance to the p-value. Now, p-value is something new. That's something you've never heard of before, unless you've taken this class before. Excuse me. But the critical values and the significance alpha, those are, we've already used them last chapter. This idea of the test statistic and the p-value, those are new to chapter 8. And in this method, well, you know what, let's not write this out. I'm going to say refer to chart. Refer to chart. Let me see. I think I have this somewhere. Okay, yeah. Let me copy this in. Copy. Okay, so we'll refer to this chart for the p-values. Now, if the p-value is less than the significance alpha, then we reject the null hypothesis. And if the p-value is greater than alpha, let's move this down just a bit. Then we fail to reject the null hypothesis. Now, this is two methods for performing the hypothesis test, but they're not, I mean, it's basically two ways of saying the exact same thing. These are not two completely separate methods, because for the last two chapters, we've been looking at the connection between z-scores and area. So the method on the left uses the z-score, the method on the right uses the area, but you can't have one without the other. If you know the z-score, you could easily find area. If you know area, you could easily find z-score. Okay, so we have Excel functions for that. We've been doing that since section 6.1. So let's look at this. Let's look at this visually. If we know a critical value, for example, if the critical value is, I don't know, let's use 1.96. Then we could figure out the area outside of that critical value. That's the p-value. And let me just pull up Excel so we could do this, but this is nothing new. This should look familiar. Okay, so we have the norm dot s dot dist. So that's our Excel function that will tell us the area to the left of a z-score. So if our z-score is 1.96, cumulative, yes. So that will give us the area to the left. We want that red area, which is area to the right. So we need the complement 1 minus. Let's round this to maybe 3 decimal places. I mean, this is an area that we should already be familiar with because it's the same area that we saw last chapter. So if the critical value is 1.96 and we're only looking at area to the right in this case, the p-value would be that 0.025. Okay, so this idea of p-values, when you see p-value or you read p-value, that means area. And specifically, what area that is, you would follow this table. So the first question is, what type of test is it? Right tail, left tail, or two tail? Now, that first question is answered by the alternate hypothesis. If the alternate hypothesis is the statement not equal to, then it's a two-tail test. If the alternate hypothesis contains a less than symbol, it's a left-tailed test. So mu is less than some number c, or proportion p is less than some number c, then it's a left-tailed test. So we're only looking at the left area. If, let me get rid of that too much red. And if the alternate hypothesis is the statement greater than, so mu is greater than some number or proportion is greater than some number, then it's a right tail test. So this you have to determine: left tail, right tail, or two-tailed. Okay, so the way you determine that is the alternate hypothesis. Okay, so maybe you're starting to see that this process of a hypothesis test is somewhat complicated. First, you're presented with the claim. Now, based on that claim, then you determine the null and alternate hypotheses. Once you have those, then it is determined whether you have a right tail, left tail, or two-tail test. So this would be a two-tailed test. Right tail if it's greater than, left tail if it's less than. Now, what I mean by left tail, right tail, or two tail, that's where your area is. And so that area is the probability of making a mistake. Okay, so just like last week with this idea of confidence, well, the alpha that we used last week was the complement of the confidence, 1 minus the confidence. So for example, what we saw last week, let me go over here. If the confidence is given as, let's say, 95%, then alpha is equal to 5%. So these two are complements of each other. Now this alpha is called the significance of the test. So in chapter 7, we use the word confidence. In chapter 8, we use the word significance. But they are complements of each other. So just like last week, in every single problem you did, you were given the confidence. So every problem last week, we're saying, make a confidence interval estimate with a confidence of 95% or confidence of 90 or 98 or 99. You were always given the confidence. Same thing this week. You have to be given the significance. You will see the word significance in every problem. Perform a hypothesis test with a significance of 5% or with a significance of 1%. So that's got to be given to you in the problem. Now, another difference that you'll see is that we're no longer using a symmetric area. Right? So in chapter 7, so let me actually come down here. In chapter 7, if you were given that the confidence is equal to 95%, then you look at the normal distribution graph. The area of 0.95 in the middle was the probability that your estimation was correct. And the other 5% was the probability that you were incorrect, and that's split between the right. So that's alpha over 2. Oh, not 0.05. It's the 0.05 is split 2.5% on the right, 2.5% on the left. Because we assume you're equally likely to overestimate as you are to underestimate. So there's two ways of being incorrect. But now in chapter 8, you're not going to be given a statement that says the confidence is 95%. You'll be given a statement that says the significance is 0.05. So normally the significance is given as a decimal where the confidence is given as a percentage, but either way, 5%, 0.05, they mean the same thing. But the difference is there's 3 different ways where that significance could be located. So that significance could be, again, split halfway, left side and right side. It could be all on the right, or all on the left. And this is what I mean by right tail, left tail, and two-tail test. So if your alternate hypothesis is the mean is not equal to some number, or the proportion is not equal to some number, it's a two-tailed test, and the significance is split between the left and the right. If your alternate hypothesis is greater than, it's a right-tailed test, and the significance is the area on the right. If your alternate hypothesis contains less than, then the significance is on the left. So two tail, right tail, left tail. So it's important to do things in order. First, you're presented with a claim. Then you set up your null and alternate hypotheses. That tells you which test statistic you're using and whether you're using a right tail test, a left tail test, or a two tail test. And then once that's set up, then step 4 is determine whether or not to reject the null hypothesis. And that's done by comparing the test statistic to the critical value or comparing the significance to the p-value. So down here, that red shaded area on each of these graphs, which comes from the significance, it's given in the problem, that red shaded area is called the critical region. Okay, so once you have a critical region, and you know where it is, where it starts, so this would be critical value, critical value. Okay, so once you know where that critical region starts, then once you calculate your test statistics, so this is what I mean, farther away from zero or not farther away from zero, to perform the test or to determine whether or not to reject the null hypothesis is to calculate the test statistic and see where it is on the graph. If the test statistic is further from zero, meaning it's in the critical region. So that's another way of looking at it. If the test statistic is in the critical region, then you reject the null hypothesis. Okay, I want to say that again because that's really the important step here. That's where you determine what to do, whether to say yes or whether to say no. If the test statistic is in the critical region, you reject the null hypothesis. So for example, let's say you set up a right-tailed hypothesis test. And for example, let's say you were given that the significance was 0.05. And let's say your critical value is 1.645. If your test statistic is larger than 1.645, then the answer is reject the null hypothesis. Now I'm just using these numbers randomly. Every problem is going to have different numbers potentially. So if the test statistic is larger than 1.645, then you would say, I am rejecting the null hypothesis. And if the test statistic is less than 1.645, then you fail to reject the null hypothesis. Okay, so let me just pause here. Does anyone have any questions? So this is a somewhat complicated topic. And so, it's not like last week, well, every other week this semester, the first section we jumped into the topic. For this chapter, chapter 8, we can't even do a hypothesis test really until next week. So section 8.1 is the pieces involved in a hypothesis test. And then next week, section 8.2 and 8.3, that is where we actually perform the hypothesis test. So it's sort of hard to get an idea of the big picture here until we have all the pieces in place. Now, the last step in the hypothesis test, so I think we're on step 4 right now. Step 1, you are presented with a claim and you represent the claim symbolically. That's step 1. Step 2, establish the null and alternate hypotheses. That determines if it's a right-tailed test or a left-tailed test or a two-tailed test. Convert the sample data to a test statistic. And then based on that test statistic, you determine whether or not to reject the null hypothesis. And then finally, once that's done, step 5, state the final solution. Okay, so rejecting the null hypothesis or not, that's not your answer. That tells you what your answer is. And to state your final solution, you are going to want to use this. So there's 3 possible results. You either reject the original claim, you support the original claim, or this hypothesis test is inconclusive. Okay, so the first question, what's the original claim? Does the original claim contain equality? So is the original claim, for example, one of these 3? If the original claim contains equality, then you move on to the next question. Do you reject the null hypothesis, yes or no? Let me try to do some color coding here. Does the original claim contain equality? Well, if the answer is no, so if the original claim is one of these 3, then you go down this path. And so if first the original claim contains equality and then you reject the null hypothesis, that puts you, for example, in this block, this first one, there is sufficient evidence to reject the original claim. So this is it. The final answer, the end of the hypothesis test, will be one of these four boxes, one of these four statements. If the problem is to do a hypothesis test, your answer is going to be one of these four statements. Okay, so this, you definitely want to have this handy when you take the exam. And this, you'll have this in my PowerPoint notes. Okay, so let's look at what a problem may look like. Okay, so this is, I'm bringing over my PowerPoint notes for this section, so you'll have these notes. So let's say you want to have a child, but you want that child to be female. You don't want to leave it up to chance, which is 50-50, give or take. You want it to be female. So you go to a fertility clinic and you pay them a lot of money because they say, if you use our method, we call it X-sort. If you use our fertility treatment, we will increase the chances of you having a girl. Okay, so that is a statistical claim. If you pay us this money and use our method, it will increase the probability of having a girl. Now there has to be some data to back that up. Okay, so in the last 100 customers, where you would expect 50 boys and 50 girls, there were actually 58 girls and only 42 boys. So there's our proof. There's our data. In the last 100 customers, there were 58 girls, meaning 58% were born female and only 42% were born male. Now the question is, so let's do some annotating here. There's your sample data. Use a 0.05 level of significance. Like I said, that's always going to be given in the problem. You're going to have to be given the level of significance to test the claim that by using this treatment, the proportion, so let's say the claim is that the proportion of girls is greater than 50%. Okay, so this is what a problem might look like. Here's a claim that's being made. The proportion of girls is greater than 50% if you use our product. We're given some sample data. In a group of 100 babies, there were 58 girls. Now the question is that 58 out of 100, is that sample data strong enough to suggest that the treatment works? Or could that occur by chance? Now, if it was 90 girls out of 100, well, that's really strong data. Or 80 girls out of 100, that's really strong data. But 58, that's close to 50-50. So now the question is that sample data strong enough to support the claim? Yes or no? Now, I try to break it down in these next slides in terms of the step-by-step method to give you a framework in terms of how to follow this method of hypothesis testing. So we start off. Represent the claim symbolically. And we did that already. The claim was that the proportion of girls will be greater than 50%. Since the claim contains strictly greater than, so let's say the null hypothesis and the alternate hypothesis. The null hypothesis is always an equal sign. That never changes. The alternate hypothesis, since the claim is greater than, the alternate hypothesis will be greater than. So you assume the null hypothesis is true unless the sample data is strong enough to cross it out and then move on to the alternate hypothesis. And then we need to take that sample data, 58 out of 100 births, and convert that to a test statistic. And our test statistic is p hat minus p divided by p times q over n square root. Okay, so the sample p, that's the 58 out of 100, so 0.58 minus what we assume is the population proportion, which is 0.5, divided by p times q over n, which is 100, and we take the square root of that. Okay, so start with the claim, then the null and alternate hypotheses. Then you convert the sample data to a test statistic. So in this case, we get a, let me go to the next slide with the answers. So we get a test statistic of 1.6. That's this, so this 1.6 represents the sample data. So now we have to determine, is that 1.6 strong enough to reject the null hypothesis, yes or no? So we saw that for the critical region, this area of 0.05 gave us a z-score of 1.645. So that's coming from equal norm dot s dot dist. Nope, sorry. So if we know the area and we want the z-score, we use norm dot s dot inv. Area to the left is 0.95. And if you plop that into Excel, you'll get the 1.645. Our test statistic is smaller. Our test statistic is only 1.6. So in that case, we do not reject the null hypothesis. And another way to come to that conclusion is to use the p-value. The p-value is the area outside of the test statistic. So if the test statistic is closer to 0, the p-value is going to be larger than alpha. So it's two ways of doing the same thing. Okay, and then we move on to our final result. What is the answer? So, question 1, does the original claim contain equality? No, the original claim was greater than. So we're down here. Do we reject the null hypothesis? No, we failed to reject the null hypothesis. So we're here. The test is inconclusive. There is not sufficient sample evidence to support the claim that's being made that this method works. Now, let's look at this. Let's look at this problem on Excel. So in the problem, we were given that out of 100 babies, there were 58 successes, 58 girls. So our sample proportion is equal to x divided by n, or 0.58. We assume the population proportion is 50% or 0.5, and Q is always equal to 1 minus P. Our significance was given as 0.5. Let's say significance. And our critical value was norm.s.inv 0.95. So there's our critical value of 1.645. Let's round that down, 1.645. And the test statistic is equal to, now we're using, let me just write this on the screen. For the test statistic, we're using the formula z equals, come back Excel. P hat minus P divided by the square root of P times Q over N. So equal P hat minus P, put that in parentheses, divided by SQRT for square root, the square root of P times Q divided by n. Okay, and there's our 1.6. Now, if the test statistic is smaller than the critical value, so what we saw is we have our normal distribution graph. We have our critical value, 1.645. And we calculated the test statistic, and the test statistic is here. It's closer to 0, 1.6. That's why we failed to reject the null hypothesis. Like I said, 58 out of 100, that's a little too close to being 50-50 for me to believe this method works. But what if instead of 58 girls out of 100, the sample data said 70 girls out of 100? Well, then our test statistic is larger. And in that case, we would reject the null hypothesis. If instead of 1.6, we had a test statistic of 4, then the answer would be, well, then the decision would be, yes, we do reject the null hypothesis. So it's all about comparing these two numbers, the critical value and the test statistic. Let me go back to the original number, which was 58. Now, obviously, as I've explained in a number of these calls or videos that I've made, if you're going to be calculating this every time you do a problem, it makes sense to save your Excel file, save your work, and then you could just replace the numbers with the new numbers in the problem. All right, so you can make this very easy on yourself by doing something like this on Excel, and instead of typing in, so like you saw when I calculated the test statistic in my formula up here, I didn't type the numbers directly into the formula. I used the locations of the numbers. Okay, and so that's the critical value method. The other method, so let me get rid of this for now. The other method is the p-value method. And it's the same graph, same numbers, same everything, except instead of comparing the two z-scores, we compare the two areas. So I mean, either way, you need the test statistic. So the test statistic is 1.6. The p-value is the area outside of the test statistic. So it's same Excel functions that we've been using. Okay, so the p-value will be equal norm.s.dist. The z-score is the test statistic, so I'll just click on B8, comma 1. That will give us the area to the left, which we don't want. We want the area to the right, so we need a 1 minus. And we don't need so many of those decimal places. Okay, so the p-value is larger than the significance, so you fail to reject the null hypothesis. So you're doing one of two things. You're comparing these two numbers, or you're comparing these two numbers. Those are the two methods, and they're not separate methods because there's this obvious connection between z-scores and areas. All right, so I mean what I just did, that's more of a section 8.2 question, but I think it makes sense to have one full question to sort of connect all the dots that we've been looking at in this first section. Okay, so that basically does it. There's one more thing I want to talk about, and that is the different types of errors that could be made. These last few slides, the effect size and Cohen's D, I'm not going to cover that this semester. So we could stop at slide 46. That should be where you stop in terms of what you need for the homework and the quiz and the exam. Now let me go back a few slides. Actually, I have it in the beginning. Okay, so there's two types of errors that could be made. And, if you think about taking, a medical test, let's say, you think you have the flu and you want to get tested to see if you actually have the flu. Well, you could walk into the doctor's office with the flu and the test says, yes, you have the flu. In that case, the test was correct. Or you could walk into the doctor's office not having the flu and the test says you don't have the flu. In that case, it would be correct. But there's also the case of a false positive and a false negative. So you could walk into the doctor's office with the flu, but the test says you don't have it. Or you could walk into the doctor's office with no flu, but the test says you do have it. So we have these two types of errors, and we call them type 1 and type 2. In this case, how they relate to the hypothesis tests is if you choose to reject the null hypothesis when you shouldn't, we call this a type 1 error, and that's the significance of the test. So we're focusing on type 1 errors, rejecting the null hypothesis when you shouldn't. The probability of that is always given in the problem, that's alpha. But a type 2 error is failing to reject the null hypothesis when you're actually supposed to. And that's called the power of a hypothesis test. That's not something we're going to really focus in on this in this class. But you could think about these errors as like a false positive and a false negative. They're related to each other. They can't, when one becomes more likely, the other one becomes less likely. So this idea of type 1 and type 2 errors, this is a small part of chapter 8. So you may see a little bit of this in the homework, but the majority of what we're doing is these hypothesis tests. Okay, are there any questions for me? Okay, so I'm still finishing up the week's page on my ePortfolio. That'll be up sometime in the next few hours. It's almost done. But, you know, I don't expect any of this to make sense yet, because there's so many parts, there's so many sort of moving parts to these problems. You'll have this recording posted on my ePortfolio if you have to go back and watch it. I mean, this is, trust me when I say this, that the way I have this laid out is a bit more straightforward than what you see in the textbook. So let me just scroll to the beginning of this test. So yes, this testing the hypothesis. So for example, this chart right here in black, this is something you're going to want to reference. I don't think this is in the textbook laid out in sort of every possible scenario on one table like this. You start with the claim, and that claim tells you what the null and alternate hypotheses are. The alternate hypothesis tells you what type of test it is, right-tailed or left-tailed. The type of test tells you what the p-value is and where the critical values are. Then you move on to the sample data. You calculate the test statistic. Whether you're using the critical value method, which is the traditional method, or the p-value method, either way, you have to find the test statistic. That's always part of it. And then once you have your test statistic, then you determine whether or not to reject the null hypothesis. And then once that's done, finally, you move on to this table for your final answer. Okay, so that does it for what I wanted to cover today. All right, so before I end the call, I know I've already asked, but any questions whatsoever before we log off?
I didn't see any of the videos on Connect. Did you say there are going to be some videos later, or there's not going to be one?
No, I said I'm still working on the page on my ePortfolio. It should be up in the next few hours. I should be done.
Oh, okay. Yeah, I just like I went to the ePortfolio and I didn't see it, so I wasn't sure like if we should just like go from the textbook.
No, it'll be up in a few hours. Yeah.
Okay, thank you.
You're welcome. All right. Good luck with chapter 8, everyone. And as always, if you have any questions along the way, please send them to me.
Okay, thank you.
You're welcome. Have a great week, everyone.
You too.
Thank you, you too.